Hello, my name is Charles Patrick in the Department of Biomedical Engineering, and I want to share with you a revision of a course where students are immersed in biomedical engineering through visual-based and inquiry-based learning. So this course, BMEN 431, entitled Biomolecular Engineering, is a senior level course. It's within the biomolecular and cellular engineering track in the program. And it really covers the fundamentals of engineering at that biomolecular level, looking at manipulation and interactions between protein, nucleic acids, carbohydrates, and lipids at the cellular and subcellular level. Again, looking also at the engineering principles of thermodynamics and kinetics. And we couple that with molecular biology. So it's a very broad course with some new, exciting applications that are developing in industry at the moment. When I took over this course, there were no learning outcomes for the class. So I set out and defined the following learning outcomes. There are three of them. One is to define and describe the biomolecular phenomenon in three different areas. And then, of course, to solve a variety of fundamental biomolecular engineering interaction problems. This aligns well with our ABET criteria as well. And then the third one was to research and obtain and critical review peer-reviewed papers in biomolecular engineering, as well as to learn how to critically review things. So traditionally, this class has been taught largely being lecture-based, accompanied with some closed-ended problem solving and some online quizzes. So this traditional pedagogy really focused on derivation equations and some underlying concepts and solving some problems. But the problem is biomedical engineering is so much more than this. And so class originally focused on just engineering principles. But biomedical engineering really takes into account three disparate fields. One, of course, is engineering principles, such as thermodynamics and chemistry and so forth. But it also couples together cellular and molecular biology. And these two areas interface and give us what the biophysics and analysis areas and how to manipulate cells and molecules within a cell. But it also interfaces with the whole field of imagination. Students have to really use their imagination to understand what's happening at the molecular level, things that we cannot see yet. And so when you couple imagination with cell molecular biology, of course, you come into the field of molecular dynamics and modeling. And then when you couple it with engineering, you get the whole field of imagineering. So really, this biomolecular engineering really is an interface of these three areas. And these are the three areas I wanted to bring out in the course with the learning outcomes. And so what I did with the traditional class was add to it visual-based learning and inquiry-based learning. So this class is a method that takes into account all four different pedagogies on a weekly basis. So throughout the week, students are exposed to this hybrid method of teaching as we go over concepts and fundamentals. The visual-based learning focused on both in-class and team activities, as well as semester-long activities. So same thing with the inquiry-based learning. There were some in-class activities as individuals and teams, and there was a team assignment as well. So the visual-based learning involved really just interacting with a bunch of tools that biomolecular engineers use in their research and in their applied engineering. Different computer models and looking at things in three-dimension protein structures and changing residues and see what happens to the thermodynamics of a molecule as you design drugs, for instance. And so students were able to have hands-on experience with these modalities. And then even doing a simple thing as DNA origami, where students put together a DNA molecule, where they could actually hold in their hand and see where the residues bind and look at the major and minor groove and have just a good, clear understanding of the physical structure of DNA, which they would use throughout the semester. The semester-long team assignment involved the students breaking out into teams for the semester, and then they would choose a biomolecular tool that is used in the area, such as CRISPR, or flow cytometry or microcell sorting, things of that nature. So they would choose a tool and then they would develop an infographic that could be used to explain the tool to individuals. And so this was a fun assignment for them. It was something different, but also had them take into account some visual learning as well as how to collapse a bunch of data quickly and distill it down to something that can be understood quickly and in a comprehensive manner. So here's just one example of one of the infographic students developed explaining how this DNA repair system worked. In addition to the visual-based learning activities, they were exposed to inquiry-based learning as well. So every Friday, we would hold a Socratic seminar where the class would be divided in two, and there would be an inner circle and an outer circle, and they would critique and review a biomedical engineering article that I chose from peer-reviewed manuscripts, and they would discuss them. It was not a debate, it was a discussion, and each week the inner and outer circle would change with each team of students. And doing this, they were able to explore different topics in biomedical engineering that were not covered in class and be able to go deeper, in addition to learning how to critically review things together. And then they also had an assignment in class where they explored intermolecular bonds, where they had class time to research bonds and then present their research in that same class period. So it was a quick research project, understanding how these bonds work among the 12 different bonds that we talked about. And team assignment was a link to the tool infographic. So whatever tool they chose here to do the infographic, they did a deeper paper research, traditional research paper as well as a team. And so this class, again, took into account all these different modalities of learning. And we assessed it to see how well the students were doing in the class. And so we developed a 54 question survey using Google Forms. Here's showing one screen of that. There were 10 sections to the survey. And we evaluated the impact of the 8 visual-based learning and inquiry-based learning activities to see how the students mastered the educational goals and learning outcomes and how they perceived they were enhancing their professional engineering workforce skills. And a traditional Likert scale was used, ranging from 1 to 5. And I was ecstatic this first semester retooling the class to see that the students did perceive that their learning was enhanced. So for instance, looking at the visual-based learning and at the inquiry-based learning, the students had very little experience, despite being seniors, in using the different modalities and different tools in biomolecular engineering listed here. And so after the course, of course, their confidence increased. As you can see, they were quite proficient. They felt confident. They understood how to use the tools and applications in biomedical engineering. And more importantly to me as a professor, they saw that their learning was enhanced by each one of these activities. So it was more fun, of course, and enjoyable for them to learn these concepts in biomedical engineering in individual and team environments through the active learning rather than just sitting there through the lectures. And they perceived their learning was enhanced by each of these activities. And here's a quote from just one of the students recently who espoused that she was excited that the Socratic seminars that the students were exposed to actually has come back to help her in graduate school, as she's able to participate and know how to critically review journal articles, and she feels more prepared than her peers. And now we also looked at 4 workforce skills, teamwork, research skills, critical thinking, and graphical tools to see how the learning activities increase those, or at least the students' perception. And as you can see, the students did perceive that these activities did increase these workforce skills. So overall, the students who originally had a little experience through these visual-based learning, inquiry-based learning activities, were able to see that their active learning activities bolstered their confidence and led to enhanced learning and the workforce skills as well. So it was a good outcome for me as a professor to see that they did perceive that their learning was enhanced. In addition, students readily acknowledged the importance of visual information and as well as the analytic and reasoning skills to engineering practice. And not shown here, but other assessments show that they demonstrate the importance of group discussion and group critical thinking skills. They appreciated that. So again, this hybrid method of combining just traditional lecture with the requisite and required, closed-ended problems, coupling that with active learning strategies, visual-based learning, inquiry-based learning, led to a more enjoyable course and enhanced the learning of the students.